This is chapter 19 for AP Chem Review on electrochemistry. To begin with, it talks about what a galvanic cell is. A galvanic cell has a cathode and anode, has a salt bridge to allow the flow of ions, and then you can calculate the cell voltage, or EMF as often is referred to as. So again, we have a zinc electrode here, we have a copper electrode here. The salt bridge allows the zinc ions and the sulfate ions to travel through because it is a zinc sulfate solution and a copper 2 sulfate solution. And the electron flow is shown there as well. So again, that's dealing with identifying the cathode and the anode to know what is the flow of electrons in this case. Standard reduction potentials is solved for with this equation. E of the cell equals E of the cathode minus E of the anode. This is something that we did spend some time on in class. The cathode is the site of reduction. So that's the first thing we have to note. When I showed you the previous page of which one is the cathode, which one is the anode, well, if you know which one's being reduced, that's the cathode. The anode is the site of oxidation. Now the easy way to remember this is cathode and reduction both start with a consonant, anode and oxidation both start with a vowel. The standard reduction table is arranged by increasing strength of oxidizing agent. So this is where we have to remember our Chem2 redox, where in oxidation reduction, the thing that is the oxidizing agent is being reduced. And if you're reduced, you're the cathode. So that's something that we have to keep in mind as we're doing this, because if you look at the table here, again, strong oxidizing agent. Strong oxidizing agent means the things that are easily reduced are up high. Things that are not easily reduced are down low. And then if things easily reduced up high are going to be the cathode. Important when we plug into that equation here in a little bit. The reduction potential table is here shown. You do not adjust for the stoichiometric coefficients. So it doesn't matter when you write these equations out if there's a 2 in front of something or a 3 for a coefficient. It doesn't matter. And you do not need to change the sign either. By knowing it's cathode minus anode, the negative and the minus part of cathode minus anode can solve anything in here, which is why the most important thing is for you to be able to identify on this table where to look. Here's the sample problem that we're going to go over. It says, what is the standard EMF of a galvanic cell made as cadmium electrode in a cadmium nitrate solution and chromium electrode in a chromium nitrate solution? So what you can do is, I'll go back to the previous slide here. First, identifying cadmium and chromium. CD and CR are the two things to keep in mind here. Secondly, the cadmium goes from a 0 and a +2 if it's with the nitrate. Here's a 0 and a +3. So if we go back to the previous table here, what you need to do is find cadmium on here and chromium on here. And whichever one's higher is going to be your cathode. Here's cadmium, the 0.40. If I look for the chromium, chromium is going to be a little further down, I believe, right here. So here's cadmium, here's chromium. Since cadmium is higher up, it is a stronger oxidizing agent. If you're a stronger oxidizing agent, that means you are going to be reduced. And if you're reduced, you're the cathode. So those are the things we have to put together when looking at this table. We don't have to worry about some values are positive, some values are negative. That's not important. What we have to worry about is identifying with this table which one is more likely to be the oxidizing agent, which means reduced, which means it's the cathode. That would be the first number we put down. So if I go back now to the problem that we have here, if you look on the board, I'm going to set it up for you. The E of the cell is the cathode minus the anode. And once again, I was able to identify the cadmium as the cathode to begin with. The chromium was the anode because of the hierarchy on that table. So this would be what we were able to do. Now the rest of the lecture here is going to be 2 equations that we did not go over in class and an explanation on electrolysis. So again, we didn't have time to go over some of these things, and frankly, I'm uncertain how much you need to know of these last couple of things. That's why I'm not going to give you a sample problem here. Instead of just introduce the thermodynamics of redox reactions. To begin with, there's a Faraday constant. Here's your joules volt per mole. And here's an equation dealing with delta G. Delta G from Gibbs free energy case. The N in this case is going to be referring to the number of moles of electrons being exchanged in the overall redox reaction. Now, overall redox reactions are things that we did where you wrote down the half reaction for oxidize, the half reaction for reduction. You add them together so the electrons balance each other out of gain and loss. That would be what the N value is referring to here. The E of the cell, I just showed you how to figure out. The F is the Faraday constant. Here's another way to solve for the E of the cell, the natural log of K, which K is going to be the equilibrium constant. So we can take that divided by our N value as well. Again, I'm uncertain if you need to use either of these equations, but at the same time our book goes over it, so I'd like to at least introduce it to you. The Nernst equation is another equation I'm uncertain if we need to do, of finding E under non-standard conditions. So the E naught is going to be the standard condition E. That's the cathode minus anode part once again. But if it's non-standard conditions, then I have to subtract from that this value here. The 0.0257 over N, already discussed what N is referring to as the number of electrons. And Ln of Q, remember Ln of Q is the reaction quotient. So products divided by reactants initially. Again, K values are at equilibrium. This is initially for the Q value right there. So two equations, these past two slides, where I'm not certain if you have to know or not, but at the same time I'd like to introduce it to you. What we're going to go over is electrolysis. And electrolysis is something that we did cover at the very end of the unit, which actually might be after you take the AP test. Electrical energy is used to cause a non-spontaneous chemical reaction. We're going to give you the example of the electrolysis of sodium chloride, and what we'll do is identify what was oxidized, what was reduced, and the overall or net reaction. And when we do that, you'll see the N value, the number of electrons, as well. So if I start off with my equation, decomposition of sodium chloride, NaCl is going to yield Na plus, I'm sorry, not Na plus, sodium ions in chlorine. Now I could balance this equation, but as you recall from redox, it's not important if we balance it. This is just referred to as the skeleton equation. A good review of redox, though, is oxidation numbers. Na starts as a +1, Cl starts as a -1. These are both 0. So +1 to 0 means it must have gained an electron. Gained electron, this is reduced. Cl going from a negative to a 0 means it lost electrons. It is oxidized. So now I'm going to write my oxidation equation first, which recall oxidation occurs at the anode. To begin with, I have Cl minus, and it's going to create the Cl2 plus a number of electrons. The way to figure out the number of electrons is first to balance this out. There's 2 chlorines here. I need 2 chlorines here. Now I have 2 negatives. Put a 2 here. That is going to be the oxidation equation. On the other hand, the reduction equation, which once again recall that reduction occurs at the cathode, is going to be the Na plus a number of electrons, making Na. Now this would be balanced right now. The problem is, in the overall reaction, it would not be balanced. So Na gaining 1 electron to become Na, that's balanced. But when you compare that with what's happening in the oxidation equation, right now I have 2 electrons here, I have 1 electron here. Which is why, to figure out my overall, I'm going to put a 2 in front of everything here. Now I can add these 2 together. And when I add these 2 together, the 2 electrons on the left side of the arrow and the right side of the arrow will cancel each other out. So my overall equation is going to be 2 of the Na plus 2 of the Cl minus is going to give me 2 Nas plus Cl2. Keep in mind the number of electrons was 2 in this case if you were to use the Nernst equation or the Faraday equation as well. And that is all that we have for chapter 19 on electrochemistry.